For a long time, the moon felt settled. Not interesting settled, but finished. Scientists argued about details, but the big picture seemed locked in. The moon formed early, cooled fast, and spent most of its existence as a quiet, inactive body. Whatever drama it once had was over before complex life even appeared on Earth. That confidence came from real evidence. Apollo astronauts brought back rocks. Those rocks were studied for decades. They told a consistent story. Lunar volcanoes shut down around 3 billion years ago. The interior lost its heat. The moon became a fossil world, preserving an ancient snapshot of the early solar system. Then China went to a different part of the moon. Not just a new landing site, but a region no one had ever sampled before. Younger lava plains. Areas thought to be geologically unimportant. When those samples were returned to Earth and dated, they did not agree with the old timeline. The moon was not supposed to be doing anything that late in its history. Yet the numbers were clear. Something inside the moon stayed warm longer than expected. Long enough to melt rock. Long enough to erupt lava. Long enough to rewrite a story that had gone mostly unquestioned since the 1970s. This was not a flashy announcement or a dramatic press conference. It was quieter than that, a slow realization spreading through planetary science. If the moon's history is wrong in this way, it raises an uncomfortable question. What else about our closest neighbor have we been confidently wrong about? Most of what we thought we knew about the moon came from a very small number of places. Between 1969 and 1972, astronauts from the Apollo program collected rocks from 6 landing sites. All of them were on the moon's near side. All of them were chosen for safety and accessibility, not for geological diversity. Those samples shaped everything that followed. When scientists dated the Apollo rocks, a pattern emerged. The oldest highland material formed over 4 billion years ago. The dark volcanic plains, called Maria, mostly clustered between 3 and 4 billion years old. After that, the moon seemed to shut down. No major eruptions, no internal movement, just impacts and slow surface weathering. This fit neatly with theory. The moon is small. Smaller bodies lose heat faster. Once the internal heat source fades, geology stops. Compared to Earth, the moon has no plate tectonics, no atmosphere to recycle material, no obvious energy source to keep things active. So the moon became a reference point, a control sample for planetary science. If you wanted to understand early Earth, you studied the moon because it was supposed to be frozen in time. But there was a quiet assumption baked into all of this, that the Apollo landing sites were representative of the entire moon. That sampling a few regions told the whole story. For decades, that assumption went mostly unchallenged, not because it was proven correct, but because there was no way to test it, until someone finally brought back rocks from somewhere else. China's lunar program was not designed to repeat Apollo. It was built to go where Apollo did not. In December 2020, the Chang'e 5 mission landed in Oceanus Procellarum, a vast volcanic plain on the moon's near side. This region stood out for one reason. By crater counting, its surface looked much younger than most lunar terrain. That alone made it controversial. Crater counts are indirect. They rely on models. Without actual rock samples, the ages were educated guesses. Chang'e 5 changed that. The lander drilled and scooped up about 2 kilograms of material, sealed it in a capsule, and returned it to Earth. It was the first lunar sample return mission since 1976. The work was led by the China National Space Administration, but once the samples were in labs, the science became global. Dating rocks is not political. The numbers are what they are, and the numbers were uncomfortable. Multiple dating methods converged on the same result. The lava that formed this surface erupted around 2 billion years ago. Not 3, not 4, roughly 1 billion years later than the accepted shutdown of lunar volcanism. That is a huge difference in planetary terms. To make lava that late, the moon needed internal heat long after models said it should be gone. Not a brief flare-up, sustained melting. Enough to flood the surface with basalt. This was not a subtle tweak to the timeline, it was a hard contradiction. Either the dating was wrong across independent labs, or the moon stayed geologically alive far longer than anyone expected. Once the data held up, the old assumption cracked. Apollo did not tell the whole story. It told the story of a few locations. Chang'e 5 showed that the rest of the moon had been keeping secrets for billions of years. The real problem was not just the age of the rocks, it was what that age implied. 2 billion years ago, the moon should have been cold inside. According to long-standing models, its small size meant heat should have leaked away quickly. Radioactive elements that produce internal heat decay over time. By that point, there should not have been enough energy left to melt rock on a meaningful scale. Yet the Chang'e samples were clearly volcanic. They were basalt, formed from molten material that rose from the interior and spread across the surface. This was not leftover heat from the moon's youth. This was sustained activity happening when the moon was already middle-aged by planetary standards. That forced scientists to revisit assumptions that had gone mostly untouched for decades. One possibility is that the moon's interior contains pockets of heat, producing elements concentrated in certain regions. Not evenly distributed, but clumped. That could allow localized melting long after the rest of the moon cooled. Another idea is that the lunar mantle retains heat more efficiently than models predicted. Even small changes in thermal conductivity make a big difference over billions of years. There is also the role of tidal interactions. Early in its history, the moon was closer to Earth. Tidal forces may have added just enough extra energy to keep parts of the interior warmer for longer than expected. None of these explanations are comfortable. They all require adjusting models that seem to work fine until real samples said otherwise. The key point is this: the moon did not quietly die early and stay that way. Its interior stayed active, uneven, and unpredictable much longer than the textbook version allowed. That means the moon is not just a frozen relic. It is a body with a more complex thermal and geological life than we gave it credit for. The moon did not change, our story about it did. For decades, we treated lunar history like a closed book because the evidence we had seemed complete. A few landing sites, a few boxes of rocks, a clean narrative that fit our models and felt finished. What China's samples showed is how fragile that confidence can be when it rests on limited ground. This was not about proving someone wrong, it was about revealing what had been missing. The moon stayed warm longer, it stayed active longer, and it did so quietly without any obvious surface clues that would have forced us to notice sooner. That should feel familiar because it is how science often works, not through dramatic reversals but through small contradictions that refuse to go away. The bigger lesson is not lunar volcanism. It is humility. If the closest object in space, studied for centuries and visited by humans, can still surprise us this deeply, then every planetary story we tell comes with an asterisk. Models are only as good as the data we feed them, and nature does not care how confident we are. The moon was never lying. We were just listening to a very small part of what it had to say.